So this is Math466, lecture. I'm confused because I'm getting box tops, which is going to make my kids happy. Lecture 14? Sounds right, 14. And what we're going to do today is we're going to do the proof of Kronecker's theorem. So the big theorem, if alpha is irrational, then n alpha mod 1 is equidistributed. Okay, absolutely spectacular theorem. This is the weakest condition that could possibly be true and have this happen, because if alpha is rational, we know we'll cycle through finitely many values. There are many different ways to prove this. Given that this is a class that has spent a lot of time working on Fourier analysis and developing that theory, not surprisingly, I'm going to choose to do the Fourier analysis proof. And so this is coming from chapter 12. And there are other ways. If you take a class with Professor Silva, he'll give you an ergodic proof of this. All right. Let chi AB of x be 1 if x is in AB and 0 otherwise. So we use this as an indicator function. So hopefully the chi's are easy enough to distinguish from the x's. If people want, I can use I for indicator. Do people have a preference for letter? I. OK. So let's do I. No problem. Now the other thing is, if we're going to fix AB throughout the whole argument, do we want to keep writing the subscript AB on I? If I was checking this for a book, I would actually create a function called, a command called IAB, something like that, and then it would always type it like that. And if I wanted to change things, I could then just dynamically change things. We will also denote this as just I of x, because AB will be fixed. And what we want to show is the limit as big N goes to infinity of the sum, n goes from 1 to big N, of I of xn divided by n goes to b minus a, where xn is n alpha. Or better yet, maybe n alpha mod 1. So what we're going to do is, for each value of n, we look at n alpha mod 1, call that xn, and we have a count of 1 if it's in our interval, 0 if it's not. And if we just take this limit, if the limit exists and equals b minus a, then that's exactly what we need for equidistribution. And this must be true for all intervals ab. The problem is, this is a difficult function to work with. If you want to plot the function, here's 0, here's 1, here's a, here's b. Whenever I draw these pictures today, I will always assume a is not 0 and b is not 1. If one of them are the endpoints, then you just have to wrap around. It's just a little bit more annoying. OK? Why is this function painful to work with? It's not differentiable. So in fact, even before not differentiable, but related to that. It's not continuous. So because it's not continuous, it's not differentiable, but it's also not differentiable. Now, why would you want something like differentiability or continuity? What theorems could we potentially use if we had a continuous function? Well, we could find minimum and maximums, but the whole point is we're trying to use Fourier analysis. What kind of theorems do we have from Fourier analysis for a continuous function? We have phase theorem if it's continuous. So if it's continuous, think Fourier. If it's differentiable, think Dirichlet. This fails both of them. But you know what? We can tweak it very easily. And we tweak it as follows. So I will draw over here, then I will erase it. This will not be drawn to scale. Here's 1, here's 0, here's a, here's b. Here is a minus 1 over j. Here is a plus 1 over j. Here is b minus 1 over j. Here is b plus 1 over j. So I'll define the function to be 1 between a plus 1 over j and b minus 1 over j, and then go straight down to a and b. So we'll call this function a2j of x. Notice a2j of x is going to be strictly less than or equal to I of x. If j is enormous, is this a big deal? No, because this is going to be a really small interval here. This is a really small interval here. It's going to drop off. OK, so it's not going to have the value 1 here, but that's going to be such a small measure, it's not so bad. Then we'll also form the function a1j of x, where I'm going to have it be 1 all the way to a and b, and then go straight down. Less than or equal to a1j of x. It goes to a minus j and to b plus 1 over j.
Not to like a and b.
Nope, it's 1.
Oh, yeah, okay.
And so in this one, now I of x is clearly going to be less than or equal to a1j of x. So if we study the sum of a2j of xn, and it goes from 1 to n, and take 1 over n, and take the limit as n goes to infinity, this should be less than or equal to the limit as n goes to infinity of 1 over n sum n goes from 1 to n of I xn, which will be less than or equal to the limit as n goes to infinity of 1 over n sum n goes from 1 to n of a1j of xn. So the limit we care about is sandwiched between these two limits. So has anybody here done measure theory? OK, so the ideas we're doing here, if you go on, you'll see these ideas all the time in measure theory. You want to prove something about a function that's like a step function, a characteristic function of an interval. That's a tough function to work with because it's not continuous. It doesn't have good properties. So what you do is you approximate it with a sequence of ever increasingly good functions that you can apply things to. And so now I no longer am working with a discontinuous function. I'm now working with two continuous functions. All right, well, are these two functions that different? No. All that's really changing is the thickness of here by what? 4 over j? I think that's what the thickness is changing by 4 over j. Something like that. At most 4 over j. Maybe it's 2 over j. We just make the middle a little bit thicker. As j goes to infinity, so that what we want to do is we want to look at this and then send j to infinity. And the goal will be to show that this limit as j goes to infinity equals this limit as j goes to infinity. And that must be this. And what do you think will show this limit equals? One times b minus a, or just b minus a, yes. And similarly, we'll show that this equals b minus a. So these will both be equal to b minus a plus something very, very small in terms of j. This will probably be a little bit smaller than this one. And then when we take the limit, they'll be equal. OK, so any questions on the general goal? We now replace studying the discontinuous characteristic function I with these two nice continuous functions. They're not differentiable. I could have made them differentiable if I wanted to, but it's fine. OK. So we're OK on this. Let's go back now. This is where more board space would be a little bit nice, but OK, we all agree on the goal. We all remember what the function is. I'm going to erase this stuff over now. And one of the things that makes this problem hard is that we have to deal with the mod. Xn is n alpha mod 1. I don't know about you, but for me, I find it very hard to just take a number and throw away its integer. If I can look at the number, sure, no problem. But when we're looking at things formally, to just throw away the integer part, that normally changes the value of a function. Do you know any functions where if you chop off the integer, it's unchanged? So I want a function such that f of x equals f of x plus 1. So where have we seen functions like this? Periodic functions. So what periodic functions do we like to look at? Sines and cosines, or the exponentials. E to the 2 pi I x. If we chose that as our function, this is also equal to e to the 2 pi I x mod 1. So this is one of the big moments in the class. This is why Fourier analysis is so useful for studying Benford's law. We want to study sequences mod 1. We take a logarithmic transform, and then we want to throw away the integer part. Normally, it's hard to throw away the integer part and understand what you have. But these exponential functions don't care about the integer part. And when we write something as a Fourier series or a Fourier series, we have sums of coefficients times exponentials like this. And so the great thing is e to the 2 pi I xn mod 1 is the same as e to the 2 pi I xn. We don't have to worry about the mod 1. Okay? Why does this matter? Well, let's consider f of x is e to the 2 pi I mx. And I'll put a subscript m to remind us that this is coming from that one. This is not the function we want to study, right? We want to study the function I, or the function a1j or a2j. But let's study this function fm. Why is this a good function to study? Well, if we can understand what goes on for this function, remember, we can build continuous approximations, good approximations to continuous functions with combinations of these. So let's see what would happen if we looked at 1 over n, the sum, n goes from 1 to n of fm of xn. And again, we don't want to use fm, we want to use either I, a1j, or a2j, but let's see what happens if we use this. This is the same as 1 over n, the sum n goes from 1 to n of e to the 2 pi I. And what does xn equal? It's just n alpha. And it doesn't really matter if we define it with the mod 1 or without the mod 1, because this function doesn't care. If we shift by an integer, how can you view e to the 2 pi I n alpha? What is this sum? This is a sum you've seen. Oh, we shouldn't have dropped the m. Thank you. The m should absolutely be there. Thank you. So you may not recognize it the way it's written. But if we rewrite this, this is a function you've seen. Or this is a sum you've seen. What's your go-to sum? I'm sorry? No. Go-to sum. If I had to give you if I'm going to give you a series to sum. Geometric. Is this a geometric series? If so, it's going to be r to the n for some r. What's the r? Yeah, so this is just 1 over n. The sum, n goes from 1 to n, of e to the 2 pi I m alpha to the n. So this is 1 over n. And now this is going to be e to the 2 pi I m alpha minus e to the 2 pi I m n plus 1 alpha divided by 1 minus e to the 2 pi I m alpha. Is this always correct, or do I have to worry about something? Yeah, if m is 0, I've got a 0 in the denominator. But I've got a 0 in the numerator. So if m equals 0, well, what would it mean if m equals 0? Well, then every term is 1. So what do you get if m equals 0? So it's equal to this if m is not 0. And if m is 0, it just equals 1. Okay, so let's look at this. If big N is going to infinity and little m is fixed, what can you tell me about this expression?
Big N goes there.
I'm sorry? Yeah, it has to be approaching 0. So why does this whole expression approach 0? I'm sorry? Well, you're looking at this expression here. Why is this expression going to 0? You know, the big N is going to infinity, which is great. Could the numerator be getting large? So how large could the numerator be? I'm sorry? 2. The numerator is at most 2. Does the denominator have any n dependence? No. So as long as the denominator is not 0, as n gets very, very large, this is at most 2 over whatever that is. Okay? This is where more blackboard space would be nice, but... So, as the numerator is less than or equal to 2 in absolute value, if the denominator is not 0, then for m not equal to 0, as n goes to infinity, goes to 0. So the only question is, can 1 minus e to the 2 pi I m alpha equal 0? Could that equal 0? What would have to be true about m alpha? Okay, m alpha could be 0. What else could it be? So if m alpha was 0, then it would work. What else could m alpha be? When else will e to the 2 pi I m alpha equal 1? M alpha equals 0. What else? So we're trying to solve e to the 2 pi I m alpha equals 1. You could have m is 0. When else is e to the 2 pi I m alpha equal to 1? When m alpha is an integer. So basically, you need m alpha to be an integer. But if m times alpha is an integer, this implies alpha is rational. Contradiction. So the denominator is bounded away from 0 in absolute value, because alpha is irrational. In a proof like this, at some point we should have to use the fact that alpha is irrational. Given that the theorem is false when alpha is rational, at some point in the argument, we should use alpha is irrational. This is where we use it. Now, m alpha could be close to an integer, and different values of m could get closer and closer and closer to an integer, which could make this denominator smaller and smaller and smaller. But as long as there's no n dependence here, we're OK. So we need some control over how close things are. OK? So what we're going to be doing is we're going to be taking a huge number of points, and we're going to look at a finite Fourier series approximation. So m will be bounded, because we're only going to use a finite approximation. And then as big n goes to infinity, then all these terms will go to 0. So what we've just shown is if we look at this function fm, then the average of fm is 1 if we take f to be the constant function, and 0 otherwise. Now we're going to do, we're going to build up a good approximation function. All right. Everybody good with all this stuff? So we understand how to do these sums with exponential functions. And that's what motivates us to apply these Fourier approximations. So by Fourier, given an epsilon greater than 0, there exists a big M such that f of x, a1j of x minus the sum, m goes from minus m to plus m, of a sub m e to the 2 pi I mx is less than epsilon. Could we do the same thing for a2j? Yeah, right? There's really no difference between doing it for a1j and a2j. So what you do is you do this twice, and then you take big M to be the maximum of the two. And this is just saying that if I have a continuous function, the Fourier series is a really good approximation. We actually know what these AMs are in terms of the Fourier coefficients. They're the weighted Fourier coefficients. So AM is going to be a1j hat of m, and then the weight will be m minus the absolute value of m over m. In particular, a0 is just a1j hat of 0. There's only one thing that I've done slightly wrong, but it's minor and it can be fixed immediately. Oh, no, actually, no. I'm sorry. It's fine as is. It's fine as is. Because Fourier's theorem gives us something that's symmetric in terms of m goes from minus m to m. So we're absolutely fine. We're absolutely fine. OK, so a0 is just the 0th coefficient. What is the 0th coefficient? So a0 is a1j hat of 0. It's the integral from 0 to 1 of a1j of x e to the negative 2 pi I 0x dx. What's e to the negative 2 pi I 0x? 1. So this is just going to be the integral from 0 to 1 of a1j of x dx. It's just the area under that. What's the area under a1j of x? I'm sorry? So we need to come back here. So we want it to be b minus a. It's almost b minus a. What's going on is we're missing half of this rectangle, and we're missing half of this rectangle. So I think that's the same as just taking this part and moving that over here, and then we're missing all of this rectangle, but then have all of that one. So we're missing a rectangle of length 1 over j and height 1. So I think the difference is just 1 over j. What's nice is this is a very easy function to find the area under the curve. It's just rectangles. If you want, you could use the trapezoid formula, where the base is b minus a, and the height is 1, and the other base is b minus a minus 2 over j. And then you could use the trapezoid formula. Okay. So what we get is that the area under the curve is just b minus a, and then we said minus 1 over j. Yes? Even if it's a 2 over j or 1 over 2j, it's not going to matter. It's something that's going to go to 0 with j. I think we actually did the calculation correctly, but I'm not too concerned. So we understand what the 0th coefficient is. The other coefficients are more complicated. Could we compute them if we needed to? Sure. But we don't need to, fortunately. Why? Because when we do the sum, we know basically that all the other sums are going to go to 0. And the only one that really matters is this. And so I'll record here that a0 is b minus a minus 1 over j. Okay. So now, if I want to sum a1j at xn, that's almost the same as summing this. Right? For each summed, what's the maximum difference I could have? So what I want to do now is I want to look at a1j of xn versus, we need a name for this function. We'll call it maybe f for Fourier, fm of x, versus fm of xn. How much could these two differ by? No, much better than 1. What do we know about how well fm approximates a1j? By Fourier's theorem, how close are they? They're within what? So how far apart are a1j and fm? How much do they differ by? They differ by, at most, epsilon. So if I then take x equals xn, how much could these two differ by? They differ by at most epsilon. So if I add up a bunch of these, the most they can differ from this, if I had 5 of these, it can differ by at most 5 epsilon. So if I look at the sum, n goes from 1 to n and 1 over n, versus 1 over n, the sum n goes from 1 to n, how much could these two differ by? Each one of these summands differs by at most epsilon. There are n of them, so that would be n epsilon, but then I divide by n. So what's the maximum difference? Epsilon. So I know if I subtract these and I take the absolute value, that that's at most epsilon. So my goal was, remember, we wanted to study the sum with a characteristic function at xn. And we said, screw that. It's not a continuous. It's not an easy function to look at. Let's look at these functions a1j and a2j instead. And we showed over here, oh good, it hasn't been erased yet. We showed over here that if we want to understand the sum of the characteristic function at the xn's, it's the same as studying these a1j, a2j's. But these functions are nicer. So step 1 was replace your characteristic function with these continuous functions a1j, a2j. Step 2 is to say, well, these a1, 2j's, a2j's, they're not particularly nice. Let me look at something that's even nicer. Because I need to evaluate the sum of this, oh Lord, at n alpha. So if n alpha happens to be in this range, okay, that's fine. But if it's not, then it's now suddenly decreasing rapidly. If it's outside, it's 0. How do I easily tell where n alpha is? But we saw that if we used exponential functions, we can evaluate exponential of xn very easily, because that's an exponential of 2 pi I m n alpha, and that's a geometric series. So the idea is we first started with I, we replace it with these functions which are easier to work with, and then we replace these functions with Fourier series. And so there'll be a Fourier series for each a. And what's nice is these Fourier series are just formed with exponentials. So 1 over n, the sum n goes from 1 to n of fm of x is 1 over n, the sum n goes from 1 to n. Oh, sorry, this is the sum of, yes, n goes from 1 to m. And now here I have a sum m goes from minus m to m of am e to the 2 pi I m n alpha. Okay? Big M is fixed. J is fixed. And then big N will go to infinity. So we will calculate this for a fixed big M, a fixed J, and let n go to infinity. What do you want to do with this double sum? So what should we do with the double sum? We have a sum on n followed by a sum on m. Almost surely, right? When in doubt, whenever you're doing anything in multivariable calculus, one of the only things we know how to do is switch sums. I have a video of Cameron when he's 2 years old. He has his bubble wand, and I train him to wave his bubble wand and say, switch sums. Have I shown you this video? He then goes crazy, and he starts running through the house yelling, switch sums, switch sums, switch sums, and just keeps running. Why did I give my son a bubble wand? Because you have to justify interchanges. So he had a magic bubble wand that he could just wave, and the summations can be interchanged. It's a very nice wand. It fell through the crack between wood boards in our deck, and it took me a long time using coat hangers to get underneath, loop it up, and get it back. So a lot of work was done for this bubble wand. It's a special bubble wand. It was his favorite bubble wand. We don't have a bubble wand. We have to justify the interchange. How do you justify the interchange? Can we switch the order of summation? So I'll start writing it because we can. What allows us to switch the order? It's, in what sense is it bounded? Yeah, there's a bounded number of terms. They're finite sums. If you only have finitely many terms, and each term is finite, you can add them any way you want. It's only when there's infinities that you have to worry. So we can switch the orders and have a sum n goes from 1 to n. And I'll move the, I'll leave it. I'll move the 1 over n. E to the 2 pi I m n alpha. And now that's the sum we know. This sum was equal to b minus a minus 1 over j. It's equal to, it's equal to 1 if m equals 0, and really small otherwise. All right, really running out of board space. At this point, I think we can get rid of this picture here. We've seen this picture enough. We're all clear on once we can show that these are converging to b minus a, we're done. All right.
Wait, sorry, what is it?
This? So this sum is equal to 1 if m equals 0, and it's something small otherwise. So that was what we proved earlier when we looked at these pure exponentials. So we get that 1 over n, the sum n goes from 1 to n of fm of x is equal to the sum m goes from minus big M to big M of A0 well, sorry. I'm going to write it like this. It's going to be A0 plus the sum M goes from minus M to M. M does not equal 0. Okay? And then for those terms, we got it was equal to 1 over n. We had a 1 minus e to the 2 pi I m alpha down below. And we had a e to the 2 pi I m alpha minus e to the 2 pi I n plus 1 alpha. So n plus 1 m alpha. So the question is, how big is this? In absolute value, this is going to be less than or equal to the sum m goes from minus m to m does not equal 0, 1 over n, 2 over 1 minus e to the 2 pi I m alpha with an absolute value. Okay? Now the important thing is, little m here ranges over only finitely many terms, and none of them are m equals 0. So this is going to be less than or equal to 1 over n, 2 times m plus 1, or oh, sorry, 2 times 2m, because I have 2m terms, and then the minimum, m, absolute value of m less than or equal to m not equal to 0, 1 minus e to the 2 pi I m alpha. Because the smallest value of this will give us the largest contribution. But because this is a finite set, this is just some number. And this is just some number. So as n goes to infinity, what does this go to? So as n goes to infinity, what do we get? We just get 0. The numerator is at most 4m. That's bounded. The denominator, it's something. It's bounded. Now, if m alpha is really close to an integer, this could be very close to 1, and this could be an incredibly small number down here, which makes this huge. That's fine. It's big N that goes to infinity. So for any fixed m, big M, this is going to go to 0. And we know this is just b minus a minus 1 over j. So what did we show? We showed the sum of the Fourier approximation at the x ends is approximately b minus a minus 1 over j. In particular, we showed that if you take the limit as n goes to infinity of 1 over n, the sum n goes from 1 to infinity, 1 to n of fm of xn, that is equal to b minus a minus 1 over j. Right? We fixed big M, we fixed j, we let big N go to infinity, and this sum goes to b minus a minus 1 over j. If we did it with a2j instead of a1j, it would be very similar. So we've now shown that this sum is almost b minus a. As j goes to infinity, it converges to b minus a. Unfortunately, this is not the sum we wanted. We wanted the sum of a1j. Well, how much can the sum of a1j change versus the fm's? Well, let's look. Thanks. We know that their difference is at most epsilon. So if we take the limit as n goes to infinity, it's at most epsilon. So we immediately get as a consequence that the limit as n goes to infinity of 1 over n, the sum n goes from 1 to n of a 1j of xn is equal to b minus a minus 1 over j plus an error at most epsilon. Okay? So what makes this proof a little bit involved is we have a lot of different things that we're fixing. We're first fixing a j, then we're fixing an epsilon, we're fixing an m, but m is actually defined by the epsilon. Once you tell me the epsilon, once you tell me how close you want to be, then we know what value of m we need. And so at the end of the day, does this see m? No. Does this see epsilon? No. This was just our first good approximation to our characteristic function. And we know that it's equal to b minus a minus 1 over j plus an error at most epsilon. If we choose epsilon getting smaller and smaller and smaller, the limit, is this limit changing as we change the value of epsilon? Does this limit depend on epsilon? No. So we can keep making epsilon smaller. That will change m. Will that change the limit here? No. What must this limit be? So what must this limit be? Yeah, it's got to be b minus a minus 1 over j. There can't be any epsilon at the end of the day. There could have been, but since this is true for every epsilon, right? So it improves itself. And then instead of getting b minus a minus 1 over j, we would get b minus a plus 1 over j for the other one. And so now we have 5 minutes. That should be enough time to just finish it off. So we're left with the following. The sum that we want, 1 over n, sum, n goes from 1 to n of I xn, and take the limit as n goes to infinity. This is less than equal to the limit as n goes to infinity of 1 over n, sum n goes from 1 to infinity of a 1j xn. And this is equal to b minus a plus 1 over j. And similarly, this is greater than or equal to the limit as n goes to infinity of the sum 1 over n, sum n goes from 1 to n, a 1j of xn. And that's equal to b minus a minus 1 over j. So we now have the quantity we want is sandwiched between b minus a minus 1 over j and b minus a plus 1 over j. So for all j, b minus a minus 1 over j is less than or equal to the limit as n goes to infinity of 1 over n, sum n goes from 1 to n, I xn less than or equal to b minus a plus 1 over j. So since this is true for all j, what's the only way this can be true for all j? This has to have some value. And we know for every choice of j, it's between b minus a minus 1 over j and b minus a plus 1 over j. What must this limit equal? Must be b minus a. Imagine it was a little bit larger than b minus a. Imagine it was b minus a plus 1 over a billion. Well, take j to be larger than a billion, and now it would be outside that range. Imagine it was b minus a minus 1 over a billion. Take j to be larger than a billion, and now it's outside that range. So the only way this can work is if this is equal to b minus a. And that finishes the proof. And we got it in before the bell sounds. Okay? There's a lot of great ideas here. This is technically a senior seminar. This is supposed to be a capstone class. We require all of you to take a capstone class as a senior to graduate. Why do we want you to do this? Bless you. We want you to see how the math connects. So we're really using a lot of stuff from real analysis here. The key idea is this discontinuous function. It's not so badly discontinuous. It's discontinuous at two little points. Other than that, it's nice and constant. We can approximate that with two very nice continuous functions. And we can make that approximation as close as we want by just ramping down how quickly we drop to 0. So we have these terrific approximations. These functions are easier to work with because we can now apply Fourier's theorem and say, rather than working with the A's, we're going to work with these Fourier series, these FMs. Why do we want to look at these FMs? Because when we try to sum the FMs at the xn's, we get geometric series. So if you want, you can title today's lecture, Why I Still Can Only Deal with the Geometric Series. And I'm a senior. Right? At the end of the day, this is the series we know how to sum. So whenever possible, we want to convert things to the geometric series because we can have this nice approximation. Lord help us if we had to evaluate the sum of sine of n or cosine of n. And you will have the joy of doing that on one of your homework problems due next Wednesday. I think I asked you to show that the sum of cosine of n to the nth power diverges. So you have to have some idea of how this function is behaving. We don't have nice closed form expressions for sums like that. But for the geometric series, we do. So whenever possible, we want to use that. And that's what's going on here, is this exponential is beautiful with respect to the mod 1. Take the mod 1, don't take the mod 1, it doesn't care. It doesn't detect a difference. So we can drop the mod 1 constraint, which we have to have, and just look at n alpha rather than n alpha mod 1. And that leads to geometric series. And then the only term that really matters is the 0th term. Now we're using the Fourier series and not the Dirichlet series. Fortunately, the 0th term of the Fourier series is the same as the 0th term of the Dirichlet. It's only as you go further and further down that you start to have differences. We don't need to have the Fourier series approximating it. We just need to have a function that we can understand. And it just needs to be a linear combination of exponentials. And that's why the Fourier series works beautifully for something like this. So what's nice is at the end of the day, we have a result that we can use. We don't need these theoretical tools and this machinery to apply it. But it's nice to kind of see what was going on and why it's true. So there is an enormous amount of rich stuff here. This is a terrific place to stop. Ponder this either over Mountain Day or day to work on projects. All right.